Okay, let's start. So this is the machine strainer kit. At the moment, we have connected the motor in series. The series connection for the motor means that it is operating in self. It is not operating in self-excited mode. It is operating in separately excited mode. So this is the fixed 200 volt power supply. This is coming from a full bridge rectifier. The full bridge rectifier takes the AC voltage coming from the mains outlet and converts into a full wave rectified voltage without smoothing. Because it is without smoothing, the average voltage is going to be around 200 volts, root mean square. So the root mean square voltage being around 200 volts is fed to the field of the motor. Separately, we are also supplying voltage to the armature of the motor. So even though this is in series mode, the voltage is applied separately to the field to excite it and then separately to the armature of the motor. So we will energize the armature of the motor slowly until we reach the rated speed. So I will turn the kit on and you can see the field current is about 0.49 amps. The field voltage is going to be about 200 volts as I said. So then we will turn the power supply on, the variable DC power supply which is connected to the armature of the kit, and start to ramp it up. As we ramp up the motor, we can see that the current is increasing on the armature as well as the voltage is being increased. The voltage is what we are varying on the armature. We can do field control, we can also do armature control. It is fine either way. In this case we are doing armature control because it is easier to control. If we do field control, the issue is that the armature might get overloaded. So we never do field control, we always do armature control. So we increase the voltage until we reach the rated speed. The rated speed will be reached at about 190 volts. So we will be measuring the voltage as well as the RPM on the motor rotor. So as we measure the RPM, we have to increase the voltage until we reach either 1.5 amps or 1500 RPM. We will reach 1500 RPM as we increase the voltage. RPM. So turn the voltage down slightly until we reach 1500. So then what I will do is I will go to the kit and then I will perform measurements. The measurements I will show you next. So now let's continue with the measurements. We'll ramp up the motor and then we'll start our measurements. So the first measurement we are making is the RPM. If you can observe the RPM, it is about 1538. That means the motor is running slightly above the rated speed. Right now, the motor is connected up to the shaft over here. This is the friction belt. This friction belt is made up of three main components. The first is the load measurement devices, then it is the friction belt, and then it is the rotor. As the rotor spins on the friction belt, it will apply a force on the motor. The more tension that is present on the friction belt, the more force is being applied onto the motor. So the next step is to turn on the load measurement devices. So right now the tension on the motor is 0, 0. So we will be increasing the tension in this manner by 200 or 300 gram steps on each of the devices. After we take our measurements, which in this case are 192 volts on the armature and then 0.45 amps on the armature. The RPM now has dropped to, it is basically the same. So the load being applied is insignificant. So insignificant load is about 0.300 gram, 0.3 kg and 0.2 kg. Then we will reset the meters and then take another reading. So either by pressing the tear button on the meter or by restarting the meters, we are going to take the next reading incrementally. So we're going to take incremental readings until we reach the rated current of the motor. So now we have applied an uneven tension of 0.34 kg and then 0.17 kg. Now we're going to check the readings on the tachometer and also on the power supply. So the RPM has actually increased, so we have to compensate by adjusting the power supply. The current has increased to 0.5 amps and the voltage is still the same on both the armature as well as on the field. So we will repeat this experiment until we saturate the motor. By saturating the motor, I mean we apply more and more tension until we reach the rated current of the motor. So this is the maximum operating mode of the motor. The RPM is 1356 and then the current on the motor is about 1.35 amps. So we're going to increase it slightly until we reach 1.5 amps. So the RPM is fairly stable at 1352 and then the current has dropped again from 1.5 to 1.24. But that is the basic procedure. So on the motor side we have F1, F2, S1, S2, A1, A2 which we have to use. F1 and F2 always have to be connected to a fixed power supply. That fixed power supply should be around 200 volts DC. You're not supposed to connect AC voltage to the field. The field should be a static voltage. But the power supply kit we have at the moment, it only supplies a rectified DC voltage, which means that it will be 120 Hertz half wave. Then S1 and S2 is present. If you want to put the motor into series mode, you have to basically put a jumper link between S1 and S2. That will allow the motor to operate in series mode. Then there is A1 and A2. If you want to use the motor only in shunt mode, you can put the variable DC power supply onto A1 and A2. Again, this is coming from a half wave rectified source. So the voltage will be 120 Hertz, half wave, half sine wave. Then there is the AC side. AC side has 3 phases plus neutral. So here it is the same. You're supposed to take your fixed 200 volts rectified DC from the trainer kit and supply it here. And then you're supposed to supply 3-phase AC plus neutral. So to control this motor, you have 2 options. You can do field control or you can do armature control. For armature control, there is an auto transformer provided in the laboratory. But the recommended way of doing control is using field control. Basically, instead of connecting the field to the fixed power supply, you can connect the field to the variable power supply. You can vary the field voltage and then the 3-phase supply can be kept fixed. That is the easier way to perform the experiment, which will skip the auto transformer completely. If auto transformer is not available, then that is the only option. The 3-phase plus neutral is connected to a fixed 3-phase supply, but you have to be extremely careful with the kit. The 3-phase supply is connected to the mains 3-phase without much in between. So there is a good chance that any mistakes can cause the breakers to trip or even cause significant fires. So you have to be extremely careful when working with the 3-phase side. Typically, the motor is not used, the machine is not used as a motor. Typically, this is used as a generator. So when this is used as a generator, you have to use the 3-phase load. So in the 3-phase load, you have again 3 phases plus neutral. So you connect the resistive load to the 3 phases of the AC machine. In this case, it will be operating in generator mode, and then the field can be connected to the fixed supply. If you want, the field can also be connected to the variable supply depending on the requirement of your assignment. If you connect the field of the generator to the power supply, then you can control how much power it is generating, and also you can control the load that is being applied onto the generator. So the higher the field voltage, the more load that will be applied onto the generator. Again, the load variation can be done using the mechanical load variation can be done using the screw tensioner. This screw tensioner is connected to the diameter of the shaft, the radius being 0.035 meters. This is the friction belt. This friction belt will apply more and more friction the more and more tension that you apply onto it. The tension again is increased using the screws. And then you measure how much tension is being applied using the 2 Newton scales. Actually, these are measuring it in grams, but it is roughly the same thing. You can convert the grams into newtons. So that is all about the kit. The tools that you will require are the control panel and this resistive load. To enable the resistive load, you have to rotate each of the switches. The more switches you rotate, the more resistors are kept in parallel. So right now, 2 resistors are kept in parallel to the 3 phases. Now 3 resistors are kept in parallel, 4 resistors are in parallel, 5 resistors are in parallel, 6 resistors are in parallel. Now 6 resistors have been kept in parallel with the load. Each of them are the same value resistor, and each of them is rated to handle 250 watts. The wattage rating is not important because the generator, whether it is DC or whether it is AC, does not generate enough power to saturate the load. So as you know, by Ohm's law, the lower the resistance, the more the load that is applied. And if you know your resistors, the more resistors you put in parallel, the lower the resistance become. So as you rotate more and more dials to the on position, the resistance will drop because more resistors are in parallel, and by Ohm's law, as the resistance drops, the current draw from the motor or the generator will be higher and higher. So that will put more and more load on the generators, whether it is DC generator or AC generator. To put the DC machine into generator mode, you have to connect the field to the fixed supply, and then you connect the armature to the resistive load. So A1 and A2 have to be connected to the resistive load in shunt generation mode. The field always needs to have separate excitation. the motor cannot handle self excitation. So we have already experimented with that, and the motor did not successfully spin while drawing a reasonable amount of current. The motor was drawing an excess amount of current, which was dangerous for the kid. When it comes to the ratings of the motor, you can observe them here. So this motor is rated at half a kilowatts or 1.8 amps. I recommend to not exceed 1.6 amps, because when you are hovering around 1.6 amps, there will be fluctuations. The fluctuations might cause it to spike up to 1.9 amps. So to stay within the motor's limit, and this motor is already quite degraded at this time, 2026. So stay up to 1.6 amps. The voltage rating is 180, but the motor requires more voltage than that to reach the rated speed. So we will increase the voltage at the armature or at the field until we reach the rated speed. The rated speed will be reached at about 192 volts. This is shunt, series or compound motor based on how we wire it up. Again, because this is separately excited, the connections are not that proper, but if you want to put it in compound mode, you can put the A1 and A2 parallel to S1 and S2. Then coming to the AC side. The AC side is also rated at half a kilowatt, neglecting the power factor, so it is in kVA. The amp rating is 0.6, so it is much lower. The field is rated at 200 volts, which is the voltage that comes from the power supply, the full wave rectified voltage, and then the current rating is 0.9 amps. So this current could vary, but that is acceptable variation. And then this is 3-phase rated 450 volts, which comes from the fixed 3-phase supply. The experiment will require you to disconnect this shaft. So to disconnect this shaft, it has grub screws. You have to untighten the grub screws and then separate the shaft from each other so it can be decoupled. Then the motor has to be run separately. So you can characterize the motor separately and you can characterize the generator appropriately. So that I will explain in the calculations part. So that is it for the motors kit. And the last thing to note is the other instrument that we will use, which is the tachometer. This tachometer, there is a button on the side. You have to press this button and then the tachometer turns on. So it will say the RPM rating as you spin the shaft. So right now it is reading 221. So the faster you spin it, the higher the RPM will be. So make sure it is on the RPM side, not on the MPM side. RPM, rotations per minute or revolutions per minute. That has to be placed on the right side or the left side here. So now you can take the readings as the generator or the motor spins. So these experiments require 4 people. One person on the RPM tachometer, one person adjusting the tension on the belt, one person monitoring the control panel over there and making adjustments, and one person to take down readings. So unless you have a total of 4 people, do not perform this experiment. This experiment is exceedingly risky without the presence of at least 4 people. It is recommended to have insulation on the terminals which are paralleled up. So this is the control panel DC variable supply on the right side, and on the left side there is a fixed supply. There are 2 fixed supplies. The bottom one is operational at the moment. The top one is not operational at the moment. Same applies on the variable supply. The top variable supply is not operational at the moment, but the bottom variable supply is operational. For most of the experiments, this is all you require. You require one fixed supply, one variable supply, and then you have the fixed 3 phases coming in. On the top, you have some measurement meters. You can use these measurement meters to make your measurements without using a multimeter. So there is current measurement, voltage measurement, then again current measurement, voltage measurement in AC, then current in AC, voltage in AC again, and a current in AC again. So these meters are perfectly operational. And if you want to slow start the motor, you also have your 3-point starter present here. This 3-point starter will put a resistor in series, so it does not kickstart the motor. It is not recommended that you kickstart the motor, but the kit is able to handle it. DOL starter is kickstarting the motor, so you can connect your 3 phases coming from the left side through the DOL starter and then to the AC side field or AC side machine in the motor configuration. This 3-phase meter also works fine, but I recommend you stick with the meters on top. But it is fine either way, whichever meter you want to use. You can also use a clamp meter for measuring current, which is recommended. So that is it for the trainer kit. There is an RPM sensor present, but the RPM sensor is not hooked up to the machine's kit on the leftmost side. So those RPM measurements on the control panel tachometer are not valid. So maybe in the next campus we will hook it up in a way that it can measure the main kit that we require. Thank you, and that is it for the hardware, and we will move on to the calculations. In this machine's trainer kit, one of the most common failure points among the circuits is the diodes burning. So if you look closely, there are 4 bridge rectifier diodes present here. These 4 diodes are connected to these wires. So there is 1, 2 input and then 9, 10 output. This circuit, if there is a short circuit present at the output, is the most likely to burn. And there are also fuses present here. These fuses are 250 volts, 5 amps. They're supposed to be, I believe, 3 amps, but 5 amps will suffice. And they're supposed to be ceramic body fuses. Do not put glass body fuses here, because the glass body fuses will not be able to handle the current. And ideally, they should also be sand-filled. So before replacing the fuse, it is ideal to break one open and then check. These are high-power 10 amp diodes, I believe so. So you can replace the bridge rectifier diodes in case it is burned. That is the most likely failure point in this kit. Welcome to the measurements for the series motor experiment. So in this experiment, there are multiple measurements we have to make. The first measurement we are making is the current going to the field of the motor. So the motor has 2 sets of windings. It has the field winding and it has the armature winding. The current is measured on both of them separately. The field current is roughly going to be the same throughout the experiment, so it is measured once and it is 0.6 amps in our case. The voltage going to the field is also the same as the voltage going to the armature, roughly speaking, so it is 192. The radius of the shaft on which the friction belt is applying force onto is 0.035 meters. And gravity is taken as a standard value of 9.81, and coefficient of friction is taken as a rough estimate of 0.6. This coefficient of friction value is not constant and it does vary, but we are taking roughly 0.6 as it gives us roughly correct answers for the calculations in the Excel sheet. Moment of inertia is not taken as that is something that is difficult to measure, and if it is measured we can incorporate that into the calculations. It is basically how much force it takes for the entire system to get into motion. So that weight is basically the wasted weight while being connected to the generator. So as you know, in the kit there are 2 machines. There is the DC machine and there is the AC machine, and they are coupled together. The friction belt is connected to the AC generator. So we have to test the motor through the AC machine. So basically there is a moment of inertia which the AC machine applies onto the motor. That AC machine's load is basically the moment of inertia. In this case we are neglecting it, though it is significant enough that it does impact the calculations. So starting with the measurements, the first measurement we make is the input voltage going to the armature and the field. This value will stay roughly the same as we are not fiddling with the voltage measurement or the voltage knob throughout the experiment. So we leave the voltage knob as is, and we have to adjust the voltage until the motor reaches its rated speed. So this is achieved at about 190 volts. So in this case we achieved the rated speed of 1500 rpm at a voltage of 192. Then we measure the armature current. We measure the armature current using the control panel ammeter. We use this to calculate the input power. The input power is basically the voltage into the field current and the armature current. So the motor is drawing power both on the field as well as on the armature. So we are accounting for both of them. Then we are measuring the load which is applied onto the rotor shaft. We cannot start the experiment with zero load. Even if we apply zero load onto the machine, there is still some dead weight present. As I said, the generator is the dead weight which is applying some amount of force. So the series motor is not supposed to be started without a load. So at least we are starting it with 400 or 500 grams of weight. This 400-500 grams is being tensioned onto the friction belt. We are using this to calculate the tension applied onto the shaft, which is the force given by S1 plus S2, which is load S1 measurement, load S2 measurement into gravity. So we're converting the weight into a force value. Then we also measure the RPM. The RPM is measured using a tachometer. The tachometer RPM measurement is slightly lower than 1500. That is because the RPM measurement is not stable. On top of that, under no load, the RPM is going to be slightly higher than when we apply a small amount of load. Here the zero load measurement is not present, but the zero load measurement is going to have an RPM of about 1500 itself. Then we use the tension multiplied by the coefficient of friction to calculate the friction force which is applied onto the shaft. This is again a rough measurement. Then we use the friction force, multiply that by the radius to get the shaft torque. That is the torque load being applied onto the shaft. Then we calculate the output power using a standard formula. This standard formula is 2 pi n into t divided by 60. So the answer is given by 2 pi speed into torque divided by 60. This output power is given in watts or VA depending on the output being AC or DC. If the output is DC, which it is in our case being a DC machine, the output is in watts. If it was a AC machine, it would be in VA. The phase shift we are not measuring at the input or the output, so we are just keeping it as 0. The power factor we are also not considering, as it is a DC machine and the output is DC, we are taking the power factor as 1. We can measure the power factor, but we have neglected to do so because we are using a resistive load to apply, we are not using any inductive load to apply we are not using it as a generator, so we don't really have to worry about this much at all. If we were using it as a generator, we could measure the output power factor and also the output phase. So the efficiency is given by the output power into power factor. So as I said, this has to do with the output power factor. We are not considering the input power factor for the sake of simplicity in the experiment, but if we wanted to, we could consider the input power factor as well. But as I said, this is a DC machine, so DC machine has a DC input, so the power factor is again 1, roughly speaking. If it was an AC machine, then yes, we have to consider the power factor to calculate the efficiency at the input, as well as we have to consider the power factor if it was a non-resistive load. So simply the efficiency is given by the output power into power factor, which is 1 divided by the input power. So we get an efficiency ranging from 8% up to 28%. These values are not very good, but as you have noticed, or as I have said multiple times before, there is a dead weight present at the output of the motor. That dead weight is the generator. The generator is also applying a good amount of load onto the machine. So that dead weight is not neglected that is not subtracted from the output power or input power. So that causes the efficiency to be measured as quiet power. But still, as you can observe, the efficiency has an upward trend up to the point at which it starts to drop in speed. This upward trend shows that the more load we apply, the more efficient it becomes because the fixed losses are fixed. The amount of power being generated is quite low, so the fixed losses appear to be quite large, which causes the efficiency to be low. As we extract more power from the system, the fixed losses are less significant compared to the output power, so the efficiency starts to increase. That's basically the reason. The ratio between the fixed losses and the ratio to the output power. So bigger the output power, the smaller the ratio of the fixed losses and the higher the efficiency becomes. So if we look at the graphs, the first graph is the armature current versus shaft torque. The more current that is supplied to the motor, the more torque it will generate, and this is roughly speaking an upwards trend. As you can see, the blue dots do not follow exactly a straight line. That is because of variation in hardware measurement. When we're making hardware measurements, we will have some amount of variation. But roughly speaking, this will be a straight line until the saturation point. So if you look at the last reading, it is not much higher than the previous reading. That means the motor is starting to saturate and it is not able to generate more torque given more power is applied to it. So again, the armature current and shaft torque is a linear upwards trend, roughly speaking. Being a series motor, the speed is quite stable. So if you look at both of the speed measurements against torque and current, they are quite stable. Both of them are quite similar. As I said, the armature current and shaft torque are quite linearly proportional until they start to saturate at the end. So in the beginning, you can see it is pretty much a straight line in both cases. So as the rotor speed increases, the armature current drawn is higher, as well as the shaft torque generated is quite stable. Then it is the armature current versus shaft torque. So as I said, the more current it draws, the more torque it will produce. So this is an upwards trend. This is similar to the plot here, the only difference being this plot is smoothless. It has less smoothing applied to it. This has more smoothing applied to it. So this is the rough trend and this is the actual measurement we got. So the actual measurement, as you can see, with less smoothing, the curve starts to saturate at the top, and that shows that the motor is not able to generate more and more torque. That basically shows that the motor is not able to generate an infinite amount of torque if you apply an infinite amount of current. Then the shaft torque and rotor speed have an inverse relationship. Basically, the faster the motor spins, the more back EMF is produced. The more back EMF that is produced, the less current is able to draw and the less torque it will generate. So basically, faster it spins, less current it can draw, less current it can draw, less torque it will produce. So at faster speeds, the torque is less. At lower speeds, the torque is more. At lower speeds, the back EMF is less, and that less back EMF causes it to be able to draw more current, causing it to produce more torque. And then armature current and rotor speed is the same relationship. Basically, the faster it spins, the more back EMF it generates. The more back EMF it generates, the less current it can draw. So this is a downward trend similar to the previous graph. Then coming to the shunt motor experiment. The shunt motor experiment has the measurements taken in the same manner. Then the output trends are similar as well. The armature current and shaft torque is a general relationship for all motors. Basically, it is an upwards trend, which is here the case. The loss in speed is going to be more in a shunt motor compared to a series motor. A series motor is able to maintain its speed better compared to a shunt motor. So if you look at the plot over here, this line is very much stable and it is not dipping below 1400 much at all. While on the shunt motor, it is going all the way down to 1300 RPM, almost hitting 1200 RPM. So the speed regulation of a series motor is much better compared to the speed regulator of a shunt motor. Speed regulation of a shunt motor. Then the shaft torque versus rotor speed, as again it shows the same relationship where the speed dips much lower compared to the series motor. Then armature current versus shaft torque is again a upwards linear relationship where the shaft current will produce more torque as it increases in its value. And that is it for the measurements. Thank you.